use the scale 1 centimeter equals 5 meters and draw the position of the drop ball at 1 second intervals. We'll start here with just our falling motion. And we can use our third equation with zero initial velocity. So we can use x equals 1/2 at. Or you can use what you already sort of know and estimate distance for a falling object. So after 1 second, we have 1 squared times a, which we're using 10, divided by 2 is 5 meters. So that's right here. We're using our scale at 1 centimeter. 2 seconds, 2 squared times 10 divided by 2 is 20. So we have a ball at 40 or 4 centimeters. And then 3 squared, 9 times 10, 90 divided by 2 is 45. So we have a ball down here, 8. And then for 4 seconds, we get 80 meters, which is, using our scale, is down here. Good. So this is how the ball will fall vertically over the course of those seconds. You can see we have uniform accelerated motion. The ball gets further and further apart. And here we do the same thing for the 4 positions thrown. This shows it thrown with no gravity, and we sort of have to add in the idea of gravity. So we're drawing the ball at the position it would be according to gravity. So after 1 second, it's gone this far in the x direction, and it's gone this far in the y direction. It's gone 5 meters. After 2 seconds, it's still dropping at the same rate according to gravity. So it's still dropping 20 meters. And at 3 seconds, it's dropping 45 meters, and 4 seconds, it's dropped 80 meters. And then you draw your best fit curve line here, like that. Okay. Estimate the number of seconds the ball is in the air. We know it's in the air for about 4 seconds. And then it asks, how is the motion in the vertical direction affected by the motion in the horizontal direction? So you can see that the motion in the vertical direction is not affected by the motion in the horizontal direction. So, whoa. All right. So this next worksheet, we have the ball being thrown downward with a certain velocity, maybe, and a certain angle. So we know that we're looking for the movement of the ball in the y direction, and we can use our kinematics equation. We have this equation shows that the distance that an object goes depends on both the acceleration due to gravity and its initial velocity. Okay, so we know due to acceleration due to gravity over time, we already saw on the other sheet that after 1 second, the ball will drop 5 meters, and then we have to add the distance the ball will go due to its initial velocity, which is given by just this sort of graphical representation. So here, the ball, we know after 1 second will drop 5 meters. After 2 seconds, we know the ball will drop 20 meters. After 3 seconds, we know the ball will drop 45 meters. And after 4 seconds, we know the ball will drop 80 meters. So we add those amounts to what we already have here due to acceleration. So we're down around 10 meters. We're down 20 meters from the spot. And from, I think that's 15 meters, we go 45 meters, so we're down to, with our scale, 12 centimeters here, and then our 80 meters plus 20 is down off the chart here somewhere. So we can draw our line starting here and going down like that. All right. And then we can estimate the time the ball is in the air, and we can see that it hits the ground sometime before this 4-second mark. So we can put 3.5 seconds there. The second question is our classic horizontal launch question that we said we'd see. So we have a car and it goes a certain amount of distance here and it drops 4.9 meters. And so we're looking for how fast the car was going when it left this spot here. So really we're looking for the initial velocity in the x direction, right? So in order to find that, like we've sort of touched on last time, was we need to find the time first. So we find the time that the car dropped from here to here. So the time that the car dropped 4.9 meters, or about 5 meters, is in our y direction. We can use the acceleration, so we're using our kinematics equations, and we find time. The time it took to drop is about 1 second, it turns out. And then using our time, we can find the initial velocity in the x direction, which we know will be constant. So in the x direction, the velocity equals distance over time, which is 24 meters over 1 second. So the initial velocity is 24 meters per second, which was the speed limit. So we could say it was going the speed limit. We have a projectile being thrown here upwards 30 meters per second with an initial horizontal velocity of 5 meters per second. So we're asked after, these are 1 second intervals, after 1 second, what is the vertical velocity? And then we're asked about the horizontal velocity. So we know that with projectiles, their motion behaves in according to acceleration due to gravity, just like it would if you threw something straight up in the air and it came back down. So after 1 second from 30 meters per second, we lose 10 meters per second due to gravity. And so we're at 20 meters per second here, would be after 1 second. And then after 2 seconds, we lose another 10 meters per second due to gravity. So we're at 10 meters per second here. And then our horizontal velocity stays constant. It's constant velocity here. So it's 5 meters per second. And then at the top of our motion, our vertical velocity is 0, but our horizontal velocity still stays at 5 meters per second. And then as we go down, we can say that our horizontal velocity stays at 5 meters per second, and our vertical velocity matches the magnitude of the vertical velocity on the other side, but changes direction. So we have 5 meters per second, and then negative 20, and here 5, negative 30. And then it gives us a hint, use geometry in our Pythagorean theorem to find the resultant velocities. So we have an x and y component, and we're looking for if if we added those together, what would the resultant velocity be? So here are your vectors again, and we have, we're looking, this is a horrible drawing, but we're looking for 5 meters per second here, and then we have 10 or negative 10, and we're looking for this. So we use our Pythagorean theorem to find the missing side. So all we're looking for is the missing side here. So we have 11.2. We have 5 and 20 here, so we use the Pythagorean theorem to find our missing side, or our missing vector. And I should put my units here. And the last one is 30.4. Word problems here where we're given an x component and a y component, and asked to solve for the rest of the motion. So number 1, a stone is thrown horizontally at a speed of 10 meters per second from the top of a cliff. So I'm going to start by drawing our drawings that we are in the habit of drawing now. So 10 meters per second is its initial horizontal velocity, and the cliff is 78.4 meters high. Okay, so how long does it take the stone to reach the bottom of the cliff? So we can solve for that knowing that the initial downward velocity of this, or the Vy, is equal to 0, and then use acceleration due to gravity to solve for time. So we use our kinematics equation, t equals the square root of 2 distance in the y direction over acceleration, and we should get about 4 seconds here using 78.4 for y. So now we know how long it's going to take the ball to drop 78.4 meters. And in 4 seconds, how far does it get from the base of the cliff if its initial velocity is 10 meters per second? And because we have constant velocity here, we can use our kind of simple equations where distance equals velocity times time. So we have our velocity and we have our time, so our distance should equal 10 meters per second times 4, 40 meters should be how far the projectile gets from the base of the cliff. All right, a steel projectile is shot horizontally at 20 meters per second from the top of a 49-meter high tower. This one has the same sort of setup. You know how high off the ground you are in the y direction. And then you know an initial velocity. So you want to know how far you go in the x direction. And to find that, you need to know how much time this whole motion takes. So you solve for time in the y direction. And you solve for x in the horizontal direction, just velocity times time. You should get 63.2 meters. So that's how far it goes in this x direction here, 63 meters. All right, number 3, a steel ball with an initial velocity rolls off the edge of a table. So same setup, we have a table that's less than a meter high, and the ball is rolling at 8 meters per second. So our time for the ball to fall to the ground will be 0.44 seconds, and then the distance that that ball goes with an initial velocity of 8 meters per second in 0.44 seconds is about a half a meter. Okay. Number 4 is a little bit different. We have a person standing on a cliff, throws a stone with a horizontal velocity. So you have an initial velocity again, and but this time it gives us how far it went in our x direction from the base of the cliff. So we want to know how far the stone falls. We want to know how high this cliff is. We have 15 meters per second initial horizontal velocity, and we have 47 meters in our horizontal direction. So what we can do with this is we can use our simple equation and find distance. So, find time using our horizontal components this time. So we have time equals distance over velocity, 47 divided by 15. So we found time using our horizontal component this time, and then we can find distance y. We have to use our kinematics equations because we're factoring in acceleration due to gravity now. And this is the third equation again with a zero initial velocity, sort of in free fall. And we get, using our time that we solved for, we get 48 meters. That's in the y up and down direction. Number 5, a projectile is launched horizontally with an initial velocity of 12.7 meters per second. So this is from the top of a building. What height is the projectile launched if the projectile lands 15 meters from the side of the building? So it's kind of similar to the one above. We have, to solve for time in the x direction, we use our simple equation again. Distance divided by velocity. And then we use that time to solve our simple equation, or our distance in the y direction using our kinematics equation. Okay, so number 5. Number 6, again, similar. We have an arrow that's fired horizontally with an initial speed. We have an initial velocity again. Fired a lot that way. And it's 1 meter off the ground. And it's asking if how far short of the target does it strike if the target's 60 meters away. So we sort of should ignore the 60 meters for now and see how far this projectile is going to go. So the first thing we need to do is solve for time. And this time we can use the y direction because we have some information there. So time is the square root of the distance in the y direction, which is 1 meter. 2 times 1 meter over 9.8 meters per second squared. And then we, using that time, solve for how far the projectile goes in the x direction. And we we should get, I think it's about 40. And then we go back and solve our initial question, which was how far short do we fall? So 60 minus 40. So we fall about 20 meters short.